We're back. I was gone for 4 weeks because I was taking my kids on a through hike of the John Muir Trail from Yosemite to Mount Whitney. Now I'm back. We did it. It was hard. And while I was gone, Eric was doing a lot of research on the theory of continental drift and the way that the scientific community did not accept or eventually did accept this theory. So I know hardly anything about what Eric has been doing because I've been gone. But I think maybe we can call this episode, Did Geologists Behave Badly? So, Eric, take it away.
Yeah, hi Sam. Welcome back from your trip. I look forward to hearing about the bear. Um, yeah, so I should say that this is a piece of scientific history I had to do uh, my own research on because I wasn't very familiar with some parts of it. I did know the broad outlines, which is there was a German geologist named Alfred Wegener. His name's spelled with a W, but it's German, so I assume it's pronounced Wegener. Uh, he published his theory of continental drift in the first part of the 20th century, but then if you talk to modern geologists or geophysicists, they'll tell you that the theory of continental drift wasn't widely accepted until the 1960s. And so, depending on how you count, there was a gap of between 30 and 50 years where there was a perfectly viable theory for this that described some very important parts of the surface of the Earth that American geologists in particular just had very little interest in. And I wanted to know what the source of that delay was. Now, it wasn't just me. I should say that I did find, as I began researching this, I found not one but two pretty substantial books on the history of continental drift that were really focused on this exact question of why did it take so long for the theory to reach any kind of wide acceptance. In particular, I found a four-volume history,
Wow.
in excruciatingly detailed research that each of the volumes was about 500 pages, and it just piece by piece. It was like why was this such a problem, and why was its adoption so slow? Um, and so what I've been researching is first, I think to understand what happened, I think it makes sense to go farther back and to talk about what kinds of questions Wegener was trying to answer, what kinds of, before Wegener came up with his theory, what was already known about the surface of the Earth. So Sam, so we're going to go back in time to around 1900, let's say. So Wegener would have been in his early training stage. People knew what the surface of the Earth looked like. They had maps of the continents. They knew where the mountain ranges were. They had no idea what was under the ocean waves. I mean, they knew where the oceans were, but no one had bothered. No one had really tried mapping the oceans in any detail yet. Um, so Sam, if all you knew, if let's say if you're a scientist and you want to try to understand the Earth, the surface of the Earth, and all you really have is these maps that show the shapes of the continents and where mountains are and where valleys are. What are the kinds of questions that might interest you?
Well, let's see. I mean, I guess, why are things the shape they are and why are there mountains at all would be one
Why are there
question.
mountains at all?
Why are there valleys at all? Why is there a difference between the land and the ocean?
Yeah,
Um,
why is there a difference? Yeah, I'll circle back around to that, but that's a good one. Um,
um,
yeah, and I think you mentioned something about why the shapes of the continents. Did I hear you say? Or
Yeah, and I think it's and again, I've read Thomas Kuhn on this, and so probably not just, I'm probably cheating a little bit here, but it sure does look like South America and Africa like nestle together. They could spoon, uh, like a puzzle.
yeah,
So some pieces of the earth that are very far apart from each other look like they would fit together if you could move them close together.
Yeah, I mean the coastlines of South America and Africa were are certainly the most obvious two pieces that seem to fit together like a puzzle. There are other parts that, if you're willing to accept some larger errors, like, do you have to bend the coastlines 100 miles? Do you have to bend the coastlines 200 miles? But the point is, it's not just South America and Africa that fit together. And in fact, Wegener ultimately argued that all the continents could be pushed together into a supercontinent if you used a little creativity. Um, so again, that's getting ahead of the story. But the question is, why do the continent? So regardless of whether the continents do fit together like a jigsaw puzzle, in 1900, you could certainly ask the question, why do the continents have the shapes and sizes that they have? Why are there these massive mountain ranges in some places like the Himalayas? Why are the Himalayas where they are? Um, why are the Rocky Mountains where they are? Another thing that I guess geologists might be curious about would be, why do you get volcanoes in some places but not others?
Hmm.
Why do you get earthquakes in some places but not
Yeah.
others?
Oh yeah,
Um,
the Ring of Fire, right? The idea that there's a
yeah.
lot of volcanism
Although
just around the Pacific Ocean.
I don't know when the Ring of Fire was I don't know when the quote unquote Ring of Fire was discovered, right? That's the idea that there are all these volcanoes and they seem to ring the Pacific Basin. And
Yeah.
there are also a lot of earthquakes along that same line. As far as when it was realized,
Oh, why earthquakes happen would be another question.
yeah, sure. Why earthquakes happen, why volcanoes happen. Um, and although if you're
Oh, oh,
if
oh,
you're
oh, oh,
if
oh, oh, oh.
oh
Sorry,
okay,
sorry.
yeah.
Because I was just doing a lot of hiking.
Yeah.
Um, when you're in a mountain range, like I was in the Sierras, um, you have these diagonal sections, and you can see these cross sections, like different colors, almost like stripes of different
Oh,
kinds of rocks, and they are
oh,
not, and they are diagonal, so they're akimbo or whatever. They're all messed up.
yeah, so if you're
They're not
walking through a canyon and you're looking at essentially a cross section through a hill or a mountain, you can see you will often see stripes of different colors of rock. Now, on the assumption that these represent layers of rock that were laid down one at a time over some historical time scale, you might expect them to all be horizontal.
right,
And
which
yet,
they kind
where
of are
you
in some place, like Grand Canyon. They're kind of like roughly
Yeah, that's right.
strata.
In the Grand Canyon, they pretty much are all horizontal.
Yeah.
But where you were, they were tilted.
Yeah. Oh,
Uh,
yeah. Big
yeah.
time. I really noticed it.
So what is going on there? So yeah, so there are lots of questions, although I mean, we might come back to this from time to time, but if you're a trained geologist, you may not be interested in any of these academic questions. If you're a trained geologist, you might actually have a much more practical concern, which is where do I find the gold?
Where's the oil?
Or moving into the 20th century, where do I find the oil?
Yeah.
I mean, you might be wondering, like, why is the oil in one place and not another, or why is the gold in one place but not another? But a more basic question is just, where do I find these things? So I mean, there's sort of two separate questions here. One is just a matter of correlation. Is there certain kinds of rocks where you can find gold or find oil correlated with those rocks? A deeper, bigger question is why do you find gold or oil in those specific locations and not others? Right. So the fact is, for instance, in the early 20th century, I found the statistic that more than half of everyone who graduated with a geology degree was just going to work for mineral and oil exploration companies. In fact, by 1950, something like more than half of all geologists were just working for oil companies. Right. So,
We were throwing the gauntlet down on these challenges.
oh wait, if
We didn't
I mean,
explain for people if this is your first episode. I'm a philosopher by training. Eric is a physicist with some biology training as well. But there's no
oh wait, so
geologist
am I
represented on this
sounding
podcast.
confrontational? Yeah, I mean, eventually I'm going to sound confrontational. Is it already leaking through?
I wondered, like they had, yeah, unlike philosophers, they have other professional opportunities. Let's put it that way.
You're talking about geologists?
Yeah, yeah. No one pays
Well,
us to
okay,
find
I
gold.
wasn't criticizing them that they left academia to get jobs. Really, this is my way of saying that because they're not in academia, the scientific explanations might not have interested them as much as
Hmm.
like it might not have interested them.
Yeah.
That's not a criticism. It's actually more of an explanation for it's or one of the explanations for why we're going to talk about this horrible lag in terms of the theory that describes the
Okay.
Earth's surface.
Yeah.
Um, okay,
Cool.
so and I mean I do feel bad for Wegener. I mean he made some bad choices that we'll talk about. Uh, but I do feel bad for Wegener because he's one of these scientific geniuses who essentially wasn't appreciated in his own lifetime and didn't live to see his theory become universally or even widely accepted. Um, and I feel, and it's you think in the 20th century we kind of had that sort of thing in its rear view in our rear view mirror, but it was still happening at least in some fields. Um, okay, so right, so let's what we're going to do now is we're going to go travel back in time to 1738.
Okay.
Okay, so this is way before Wegener wasn't born till the late 1800s. So I want to set the stage for Wegener's academic training. Okay, so 1738, there was a French geology mission to Central and South America. I mean, they had several interests. They were interested in carefully determining the shape of the Earth. It turns out the Earth isn't a perfect sphere. It bulges slightly at the equator, and there are some other things they were interested in. Um, and the mission included someone named Pierre Bouguer, who was a French physicist, a French explorer named Charles Marie de la Condamine, who's famous for other reasons, and a Spanish Navy officer who just happened to be part of the team, and his name was Antonio de Ulloa. I'm going to say Ulloa, but it's probably Uyoy or Uyoa. But the person who gets credit for the discovery we're about to discuss is Pierre Bouguer. Okay, so in 1938, give or take, Bouguer and Le Condamine and a group of assistants who they hired from the local communities decided that they were going to climb the outskirts of Mount Chimborazo in Ecuador,
Hmm.
and they were going to try to measure the or measure the gravity of that mountain. Okay, so
Okay. So I know about Mount Chimborazo or Chimborazo.
please, I could be mispronouncing it. In fact, I'm going to
Yeah,
mispronounce a lot of stuff this
that's
episode, I'm
that's
sure.
okay. There's other videos where they pronounce things correctly. We don't have to
Okay.
be one of them. So if I'm right, I think that Mount Everest is the tallest from base. Hold on. Chimborazo is arguably, in one definition, is the tallest mountain on Earth
Oh, really? I
because
didn't
the
know that.
tip of it is the furthest from the center of the Earth. So if you're measuring the height of a mountain to the center of the Earth, because it's on the bulge, it's on the equator, it is
Oh,
further from the center of
okay.
the Earth than the tip of Everest is.
Oh, interesting.
But Everest, is like higher
So
up
Everest
into the
is the highest
atmosphere.
above sea level, but
Right.
sea level follows this weird bulge, right? Sea level is in some
Exactly.
sense higher at the equator.
Yes, that
Okay.
is correct.
Oh, I did not know this. This is an interesting
Yeah.
factoid.
Right. And then Mauna Kea is like the tallest from the base since the base is under the sea. So
Right.
it's tallest from the base. So those are the three tallest. So that's what I know about Mount Chimborazo.
Chimborazo, you're saying?
Chimborazo. I don't know.
Oh, okay. I mean,
Yeah.
okay, we're just gonna. I think
Yeah.
every time we say it, we should just come up with a new pronunciation for it.
Yeah.
Uh, okay, so Pierre Bouguer wanted to. I mean, they were doing other things, but they wanted to take some time to see if they could measure really the I want to say the mass, but really the gravity of this giant mountain that rises above the plains of Ecuador, and um, and now, again, Newton had already a long time earlier. Newton had published his theory of gravity that said that any chunk of matter in the universe attracts every other chunk of matter in the universe. We tend to think of gravity as being just due to the Earth because the Earth is the biggest collection of matter in our neighborhood. But Newton's theory of gravity says that if you were to get close to a big chunk of rock, like say a mountain, it should exert a not a, it should exert a small additional gravitational attraction, roughly sideways. Okay, so the idea would be, I mean, certainly the expectation of this expedition was that if you just take a string and you hang a mass straight down, now away from a big mountain, that string will point right to the, let's call it the center of the Earth. The technically minded audience members might know it doesn't point exactly to the center of the Earth because of this bulge at the equator, but we're not going to worry about those details. Right. So if you just take a mass and on a string and you let it hang still, the string points right to the center of the Earth. But near a big mountain, the expectation was that the mountain's gravity would would pull on the mass sideways just a little. And so there'd be a tiny angle between the string and the down and the center of the Earth. Okay. And this team, they had very precise tools for measuring these tiny deflections from the vertical. Basically, I'm not going to get into too much detail, but basically they would calibrate their instrument at night by lining up the top of this, it's called a plumb bob, lining up the top of this bob with distant stars. So they could figure out exactly what angle the local down should be. And so they go through all this effort. It was snowy. One of the explorers, I think he twisted an ankle or something. He had to go back down the mountain. It was snowing much more than they expected. They were generally very unhappy people. They went through all this, and they thought they were going to be able to measure the mass of this mountain. And having gone through all that work, what they discovered was, Sam, do you happen to know what they discovered? I mean, you can hear what I'm
No,
building up to.
no, I don't know that. I don't know. I don't know. I have no
I
idea.
didn't know the story either until I started researching this. What they discovered was no deflection at all, zero.
Yeah.
I mean, they found they found a tiny deflection, but it was within their error bar, within the error of zero deflection at all. Um, and and they were very, I mean, I would imagine they were pretty disappointed, but they were, faithful scientists. And when they got back to France, they published their results. So the book came out about 10 years later, and they said, look, we climbed the mountain, we set up our plumb bob, but we got no deflection at all. I mean, you might think, oh, what are some of the crazier explanations for this? Maybe. Oh, actually, Sam, you're the philosopher. Do you want to come up with a crazy explanation for this, or do you?
There was another mountain they didn't know about on the other side of them, just beyond the
Sure.
horizon.
Okay.
I don't know. Or
Yeah, maybe
there
there's
was
another mountain.
yeah, or on the other side there was like a big deposit of lead
Oh,
that
okay,
had
that's
gone
not
through.
bad.
Yeah, it's not too
Actually,
crazy.
that's a pretty good one. Or maybe Mount Chimborazo is hollow. I mean, but so they published the result, and people didn't know how to interpret it. It was just one result, but then over the next 100 years, different teams all over the world kept trying this to measure mountains, mountain ranges. I think a British team tried measuring the mass of the Himalayas. And although they would get small non-zero results, they never got anywhere close. Like they were getting like just a few percent of the mass that they were expecting based on, the mass, the density of the rocks and the size of these mountains. And so the answer came, or an answer came around 1850, about 100 years later. I think he's a British mathematician named George Airy, who, in my physics training, I encountered because he also did a lot of work with optics. Okay, and George Airy said that the reason these mountains don't seem to weigh anything is, and he actually, I don't know that he argued using this analogy, but I'm going to argue the following analogy. Let's say you're going to measure the mass of an iceberg that's floating in the ocean. So you go out to the iceberg and you set up a little platform near the iceberg and you set up your plumb bob. It turns out that plumb bob also will not see most of the mass of the iceberg. I don't know if it's exactly zero. I think it'll probably just be close to zero. Okay. And And the idea is that even though the part of the iceberg above the water is way more massive than the air that surrounds it, the iceberg sits on top of an even larger chunk of ice that is less dense than the ocean water that surrounds it. And those two, and so that even though there's an excess of mass above the waves, there's a deficit of mass below the waves.
Hmm.
That because of because of buoyancy, those two, the excess above and the deficit below, exactly cancel.
Hmm.
Um, and so Airy said, you know what? I think the interpretation here is that tall mountains must have deep roots that are actually less massive than the surrounding rock.
Hmm.
And we now know this is correct. But this he was the person who first suggested it.
Wow. Okay.
Um, okay, and but it
That's really
goes.
cool. I mean,
Oh,
it
okay,
takes me a while to think through it, but
yeah. I mean, this is. I mean, to me, I feel like geophysicists by not. I mean, to me, this is a fascinating story, and I don't think it's well known.
yeah.
Um, but I feel like sometimes maybe geophysicists have because they're inside their field. I think they might have some trouble seeing what an outsider would find interesting. But to me, the idea that mountains have almost no weight. It's an illusion in the same way that an iceberg would seem to be almost massless.
It's like a net. It's like their net weight is zero, even though
Yeah.
obviously,
But
if
to
you
put it
chop
more
off the top
plainly,
of a mountain and try to lift it up, it would be heavy.
yeah. I mean, but to put it more plainly, Airy was saying that mountains and therefore probably whole continents are floating, literally floating in heavier rock.
Hmm.
And again, we now know that this is true. But he was drawing this conclusion just from these plumb bob measurements.
Huh. Well,
Um,
if I can point out, that's a great
yeah,
example where a null result that seems disappointing is actually a great clue.
yeah, that's another fun part of the story. Oh, someday maybe we should do a whole episode on just null results,
Yeah,
actually.
because that's,
Um,
people, oh, I didn't get anything. I won't publish it. Well, this is a great
yeah.
example where it led to this discovery.
Oh, yeah, yeah, yeah. Yeah. So let's not forget that could be a really good episode. Okay, so the of course because we're scientists, we had to give this a fancy technical name. The idea that continents and mountains are floating in a sea of heavier rock is was called ultimately it was called isostatic equilibrium, or just shortened to isostasy.
Hmm.
But basically just equilibrium. The idea is that continents are floating in heavier rock. Now, the implication here, though, is that I mean, there's a lot of implications here. One is that continents are somehow different from the rest of the rock that we might find on Earth. And so this brings us to something that we haven't actually discussed yet, which is that the Earth is actually in terms compared to every other planet and moon in the solar system, the surface of the Earth is very unusual. And it's very unusual because it basically has two different levels with not a lot of middle ground. Okay, so one level is the level of the continents themselves, which happen to be above sea level. And the other level is, we don't tend to think of it this way, but the other level is basically the bottom of the ocean. So continents, despite the fact that there are mountains, continents tend to be mostly flat, and the sea bottom tends to be mostly flat. And the difference between those two levels is I forget. It's like, but it's more than a mile. It's like 2 miles, right? So although if you remove the oceans, what the Earth is it's a bunch of massive plateaus, essentially the largest plateaus in the solar system.
Hmm.
And all the plateaus everywhere on Earth are roughly the same height, because if they weren't, some might be below sea level. And there's no continent below sea level as far as we know. Right. So the Earth is two levels. There's two levels that are separated by this massive difference. And so this is a more modern result, but I'm going to introduce it here. And so what we now know is that the continents, they are made of distinct rock. But it's not just that they're made of distinct rock. They are giant chunks of rock that everywhere on Earth they have roughly the same thickness and roughly the same height above the sea bottom, And honestly, mountain ranges are a relatively small correction to that total. Um, but the outlines of these discoveries happened in the 1800s. So after Airy proposed his theory, other people, I mean, I think there were competing theories, but I think at least in Europe, the idea of isostatic equilibrium, the idea that mountain ranges and continents might have deep and relatively low density roots. I think that I don't know that it was a minority view. It certainly didn't win 100% approval, but it was a widely accepted theory by people who by people who were a little forward looking. There was and continued to be a competing theory for literally everything that we've been discussing. And I should mention it here, which is, here's the thing, isostasy or isostatic equilibrium, it doesn't seem to explain mountain ranges. It doesn't seem to explain the shapes of the continents or why they are where they are. So there are things that isostatic equilibrium doesn't seem to be able to explain very well. Um, and so it did have a competitor, which I don't know what its exact name was, but I'm just going to say the competing theory was the theory of thermal contraction or global contraction. Basically, the idea is that the Earth formed and it was hot, and then over time it's been cooling off. And as materials cool, they tend to shrink just a little, but enough that if you have a chunk of material as big as the Earth, as it cools off, it'll shrink in a significant way. And so this, for instance, could be a really nice explanation for things like continents and mountain ranges, because if you have a sphere which is gradually shrinking, but it has a relatively brittle crust covering it, which isn't shrinking, isn't participating in that shrinkage, then as the interior shrinks, the crust will buckle in a set of patterns that look a little bit like mountain ranges. Right. So this was the competing theory, and although it might not explain it might not explain this result with the gravity of the mountain ranges. At least it explains why there are mountain ranges in the first place, which isostatic equilibrium couldn't do. Okay, so in the mid to late 1800s, these. Oh yeah, go ahead.
Well, I was just going to say something, and again, at some point we should talk about ad hoc hypotheses. But if an ad hoc hypothesis is a hypothesis that you don't have independent evidence for, that you're using to explain a problem in your observation when you didn't observe what you thought you would observe, then the kind of hollow roots theory is an ad hoc hypothesis because you have a well-confirmed theory of gravitation. You didn't observe what was expected from that theory. And instead of throwing away the theory of gravitation, which
Right.
obviously has
Okay.
immense support, you say, oh, well, maybe this is what's going on. And you hypothesize that something that you can't observe is going on a one-off basis.
Yeah.
And in philosophy of science, that those are usually seen as the enemy. They're bad. But this is a
Yeah.
really nice
Actually,
example where it was correct.
but actually, I will throw in that I'm not sure anyone had measured gravity between any two objects that weren't astronomical in size.
Yeah.
The actual force of gravity between two lead balls is so weak that it wasn't. I think it wasn't measured till the early 1800s.
Hmm.
So in this, yeah, that's right. That's right. So in the, oh yeah, no, but it was measured in the early 1800s. So um, certainly in the 1700s, you could argue, well, we don't know that gravity works exactly correctly on the surface of the Earth. But by the 1800s, we did know that gravity, like you could measure gravity in a lab if you had a very careful way of measuring the force between two large cannonballs, basically. Um, so you couldn't argue that gravity didn't work on the surface of the Earth because we already knew that it by 1850 we definitely knew that it did. Um, but yeah, it's still easy to imagine. One could still try to imagine other possible explanations for this mass problem without invoking the idea that a mountain is like an iceberg. I mean, that is a really big ad hoc hypothesis.
Yeah.
Um, I mean, yeah, it requires, yeah, it really does require a visual imagination. On top, it requires a visual imagination that somehow, I mean, what it really is saying is that wherever we have a mountain range, there's also kind of there's a route to it that extends deeper than the mountain range extends upward. I mean, yeah, it's true. That is a pretty extraordinary claim if you have no other evidence for it.
Yeah.
Um, I
But
mean,
it seems like it worked well to have as part of scientific method to propose this ad hoc hypothesis and then evaluate it. And the
yeah,
other
but I
one
mean, I
is
think,
less ad hoc because it explains more, but it turned out not to be correct.
yeah, I mean, but I think you're right. I think we do need to focus on, I mean, it's easy to stand here in the 21st century and say we know which of these theories turned out to be the right one. But yeah, I mean, that's why in fact, this is what, but yeah, I think it's important not to bring our present understanding of the surface of the Earth into our attempt to understand the history of these discoveries. Um,
Okay. Well, sorry for the interruption. Go ahead
no, no, I
with
mean,
the story.
yeah, um, yeah. So, okay, so I think we're ready now. Let me see. Actually, yeah. So there was one more thing. But there was another interesting discovery related to isostatic equilibrium, and this happened in the 1890s. So there was a Swedish geologist, and he found these essentially not quite fossilized beaches. He found these rocky slopes. So beaches that weren't sandy beaches, but just beaches where the ocean met these rocks. Um, and there were these weird linear striations across the rock, just sandwiched like one after another. But they weren't the layers that you were talking about. Instead, these seem to just be erosion marks left by where the ocean was crashing onto this shoreline. But the crazy thing was that these beaches, they had these horizontal lines, they had these erosion marks, but some of them were well above sea level. I don't know how high up they go. I saw some photos. It looks like some of them go up 50 or 100 feet. And so he concluded that either the ocean was 50 or 100 feet higher in the past, or, and this was his claim, that for thousands of years, these beaches have gradually been lifting up over a distance of 50 feet or 100 feet. And he said, well, why? And these weren't just the beaches. He's saying the entire Scandinavian peninsula, all of Norway and Sweden, has gradually been lifting up over thousands of years. And he brought in this idea of, so Sam, do you see how that might be connected to isostasy or isostatic equilibrium? I'll give you a hint. It has something to do with the ice ages.
Okay. No.
Yeah, it's not an easy connection, right? So here's what, but he already knew about the ice ages, at least in broad outlines. So the researcher's name, I'm not going to find it quickly, am I? Oh, here we go. Swedish geologist Gerard de Geer. He said, you know what? We know that there was an ice age, maybe 10,000 years ago, 15,000 years ago, when the Scandinavian peninsula was covered with maybe as much as half a mile of solid ice. And half a mile of solid ice weighs a lot. And so he said during the ice age, all that extra weight would have pushed the continental rock that composes Norway and Sweden down into the surrounding denser rock. It would be like if you started stacking boulders on top of an iceberg. The iceberg would start sinking a little bit lower in the surrounding ocean. And then if you remove those boulders, the iceberg would rise back up.
Mm.
I mean, by analogy, he said, when the ice age happened, all that extra ice, the weight of all that extra ice literally pushed down the Scandinavian peninsula into the surrounding more dense rock. And then when the ice age ended and most of that ice melted and flowed into the oceans, the Scandinavian peninsula has ever since then, for 10,000 years or 15,000 years, the Scandinavian peninsula has been gradually rising back up. And it's not, according to what I read, it's not done. Every year it still rises a little bit more because it takes because the surrounding rock, it doesn't flow the way water flows, right? I mean, whatever that surrounding denser rock is, it moves really slowly.
Hmm.
So it takes way longer than 10,000 years to restore this mechanical equilibrium that is normally maintained. And again, this is an explanation that we now know to be correct. But it was discovered in the 1890s when Wegener would have been in his teen years and beginning to learn science. So yeah, so from Airy we got the idea that continents are less dense than the surrounding rock and that they're sort of floating. But then we have additional evidence that I mean that floating is itself a kind of mechanical equilibrium and it can be perturbed. You can push down on a piece of continental rock, and when you let it go, it will gradually float back up. And all of this was known as Wegener was going through his training. So he was born in 1880. And so he would have grown up being taught or learning about these basic ideas. So again, the isostatic equilibrium offers us no explanation for mountain ranges, but it does seem to explain these sort of physicsy observations. And so this brings us to Wegener's professional life. How are we doing so far?
Oh, I think I'm entranced.
Okay.
I'm looking.
Right. So this brings us to Wegener now. So Alfred Wegener, German, he's if you look at his Wikipedia page, he's got lots of different professions, which actually may have worked against him in the long run. But he's famous as for his geology work, for proposing the theory of continental drift. He was a meteorologist. He was an Arctic explorer. He was a jack of all trades. And so I think but he had some pretty substantial physics training. So he understood. So I think he was one of these people who had a good technical background and gradually began learning about more interdisciplinary topics as his interests shifted from time to time. And so I think he was around 30 in around 1910 when he was looking with some friends at like a map of the Earth. And he thought, isn't that interesting that the coast of South America seems to fit so neatly into the coast of Africa. And I don't know that Wegener says this outright. I mean, he wrote a book eventually. I haven't done all of this research, but I guarantee you what happened that Wegener already thought of continents as chunks of rock that were floating very, very slowly, but floating in a pool of heavier rock. And so I think the logical connection was if these two floating rocks look like they fit together, then in the past, maybe they really did fit together. Maybe they were literally right next to each other. And then that piece of continental rock split in two. And then gradually these two floating rocks drifted apart from each other. And that was the core idea. So I think, again, the idea that he grew up with the idea of isostatic equilibrium, and I think he probably internalized it. And that was what allowed him to make this extra leap of genius to suggest that the continents really do drift from side to side rather than simply up and down. And I mean, so that's the core result in a nutshell. He noted that he argued as early as 1915 he went public with a talk, and maybe I don't remember when the first edition of his book came out, but around 1915 he went public with this idea that I think is generally called continental drift. That there was a point in the Earth's past when all the continents fit together into a sort of supercontinent. Now, he didn't have one piece of evidence. He had lots of evidence, right? So between his initial burst of insight in 1910 and the time he went public around 1915, he looked into paleontology, he looked into geology, he taught himself about plants and animals and extinctions. And everywhere he looked, he kept finding additional evidence that South America and Africa in particular, but really also North America and Europe, used to be much closer together. And he would argue were literally connected to each other with no Atlantic Ocean. So in the past, there was no Atlantic Ocean at all. And so some of the evidence was there are there are we talked already about the fact that there are different rock. If you dig down, there are different rock layers called strata. And so in the 1800s, the science of stratigraphy was already well established. And so it turns out that if you look through at the strata of rocks on the west coast of Africa, and you look at the strata of rocks that you encounter on the east coast of South America, very, very similar. Okay, so so it wasn't just that the outlines of the two continents fit together. The actual kinds of rocks and their relative ordering were very, very similar on the two coasts. The fossils, not all, not the if you go back far enough, the fossils in these strata
Mhm.
are essentially identical as well. Right. So one of the ways that you can identify the strata of rocks is if they're fossil bearing strata, then right, different strata contain different fossils because new species arise and old species go extinct. So, I mean, can you imagine? I mean, this must have been, I mean, this is, can you imagine just starting with the initial observation that South America and Africa seem to fit together, and then actually doing the research and discovering that the fossils match up across these
It's
two
wild,
coastlines?
right? And what I love is it's so many different kinds of science, like
Right.
biology and paleontology, and it's not just geology. So it was very interdisciplinary among the sciences. And then you conclude the Atlantic Ocean used to not exist. I,
Yeah. I,
it, when Earth did, obviously, at some point it
yeah.
didn't exist, but
Yeah, I mean, between 1910 and 1915, that must have been I mean, the excitement that he must have felt. It's hard to imagine. I mean, I've had moments of scientific discovery, but I mean that, the case that the Atlantic Ocean is not as old as the Earth and that it used to not be there. I mean, that's such an extraordinary thing to say. Um, so his initial lectures and then the book when he published it basically point all this out. He doesn't just remind people about isostatic equilibrium. He doesn't just point out that the continental outlines match. He makes all this. He points out that look, the fossils line up and the strata line up. And actually, I did again. I don't know all the details here, but there are also some modern animals which are clearly descended from ancestors. They're modern animals that descend from a common ancestor which that common ancestor clearly existed in both South America and Africa in the distant past, right? So in other words, there's I wish I could remember. I didn't double check this piece of the story, but there is some evolutionary evidence as well that using modern animals or maybe modern plants, certainly that Africa and South America used to be adjacent. So he pulled it all together into a book, and uh, despite what seems to us to be a rock solid case, oh, pun intended, uh, um, he was not met with universal acclaim, to put it mildly. Um, and so I mean, some people were convinced right away, but it remained a minority view throughout Wegener's lifetime. So Wegener died in 1930. That was the last edition of his book. And yeah, as late as 1930, American geologists had absolutely no interest in the theory, and even European geologists. I mean, some of them were convinced, but an equally large number were still very fond of the shrinking Earth theory, because at least the shrinking Earth theory explained what mountain ranges were doing there. Right. So, I mean, there were things that the shrinking Earth theory seemed to, like the shrinking Earth theory seemed to offer a really obvious explanation for earthquakes too, right? Um, and and so yeah, so Wegener did not live to see the acceptance of continental drift, and in fact, the idea of continental drift was always a minority view. So I mean, I feel bad for the guy. I mean, I
yeah.
shouldn't. He was a successful scientist, and he was had many professional successes. He died young. He died at age 50. He died on another Arctic expedition. it is what it is. But so what I want to do now, though, is right. So this was actually my starting point for researching this podcast, which is why why was there so much initial resistance to the theory, and why even in the 1950s it still was not making any it still was not making any converts in the American geology community.
Mm.
Okay, so um, all right. So I've made kind of a list of problems, or which some of which had to do with Wegener, some of which had to do with science at the time. I'm going to say that problem number one was that he was German, a German scientist who published his theory in 1915.
Okay,
Right. So, Sam, can you see why that might be a problem?
I do. I can get this one. So World War One, I mean, America was not in the war yet in 1915, but obviously uh, had it, most Americans would have been on the side of the not Germans.
Yeah. Yeah, and I mean, Einstein did publish some of his important work in 1915, and Einstein was working in the German-speaking world, but um, Einstein was also a famous pacifist, and whereas Wegener was in the German army in World War One, and he participated in, I think, several parts of the early
Yeah.
invasion of Europe. He was injured in action, and I don't know whether he was honorably discharged or just moved to a different branch of the German military, but he became a meteorologist who, among other things, did continue working at least in part for the German military. So I think that was from the perspective of American scientists. I think that was one strike against him. I mean, again, I'm guessing no one ever went on record, like no one ever wrote, "Oh, we should reject this theory because he's in the German military." Um, but I'm guessing that this was not a point working in his favor. A second problem was, as I've already mentioned, he was very interdisciplinary. He was never just a geologist. He was always interested in many different things, and even the interdisciplinary nature of the book that he wrote, right? It dragged in botany and paleontology and stratigraphy, and the fact is that I mean, he was an enthusiastic amateur for a lot of these, but he was still ultimately an amateur. He didn't have a PhD in paleontology, for example. So working against Wegener was, first of all, that he was a German-speaking scientist and an ex-German military officer publishing his results in 1915. Another was the fact that he was interdisciplinary. So it's easy to imagine that in the first edition of his book, there were probably little mistakes, right? I mean, he admits this, right? I mean, so if he's talking, for instance, about the different layers of rock in the African coastline and the South American coastline, it's super easy to imagine that maybe he used outdated terminology, or he got the order of layers wrong, or I mean, there are lots of little mistakes essentially a gifted amateur might have made. Therefore, if you're a paleontologist and you're trying to read this book, you're going to focus on the paleontology mistakes. And if there are enough of them, or if you're already predisposed to rejecting this theory, then it's going to convince you that you should just ignore this book and put it down. Right. So the fact is he was making an interdisciplinary case in many fields that were not used to working in an interdisciplinary way. And then I think that so let's see, the German speaker during 1915, interdisciplinary arguments, admitted probably some small, but probably I would say ultimately inconsequential mistakes, but mistakes that wouldn't have felt inconsequential to a botanist or a paleontologist at the time. And then again, as I've already mentioned, that American geologists in particular were very focused on what you might call the engineering aspects of geology, which is to say, oil and mineral exploration. And so I think certainly on the American side of the Atlantic Ocean, I don't think there just wasn't much interest in the what I would now call geophysical theory, or just the field of geophysics. The field of geophysics barely existed, and at some level, that's what Wegener was. He was a geophysicist. Um, so for him, I think he was like to him, he was an expert in geophysics. He had physics training, and honestly, meteorology involves concepts like buoyancy, right? So he was an expert in those pieces of the story. And so for him, the fact that he found supporting evidence from all these other fields was just icing on the cake. Um, but that's not how everyone else saw it. So yeah, I think, but to give you the flavor of some of the objections, Sam, open up. I think I shared with you on Google Drive.
Oh,
It's a paper from 1924.
oh yes, I have it
Can you just
in
open up that?
science.
Yeah, from Science Magazine, which is of course an American science publication from I think it's 1824. And then can you just read off the headline?
Germanic pseudoscience,
Yeah.
which I mean, why call it Germanic, right? So that
Yeah,
lends
right.
support for.
Yeah, absolutely, right. So this is a book review. I guess there was a German botanist who wrote a whole book in support of Wegener's theory of continental drift. Um, but this was a review of that botanist's book by I think an American or British botanist. And yeah, I mean, so if you dig into the details, which we're not going to do, they highlight a handful of small mistakes
Oh
in
yeah,
Wegener's book,
it's true.
right? Yeah. But I mean, they don't set out to criticize the geophysics. They don't set out to criticize isostatic equilibrium or the facts that overall this, they just pick on a few tiny details.
Yeah,
But yeah.
even before the internet existed, they were doing
Oh,
this.
do you
This
want
is
to
like an
elaborate?
internet thing. Like, oh,
Yeah,
but
it
there's
totally
this little
is.
problem here and missing the main point.
Yeah. This is totally a kind of internet trolling of Wegener's theory. It's like rather than engaging with any of the substance of what he's claiming, they happen to find a few small errors. They wrote a book review. They got it published in Science Magazine, which was already becoming one of the most important magazines in at least in American science. And then they gave it the absolutely insulting title, not just of pseudoscience, but Germanic pseudoscience. And anyway, so this is right. So I think so. This is episode one of this two-parter. In part two, we will come back to this part of the story and we'll go forward and we'll talk about how Wegener's theory eventually did achieve universal acceptance. But for today, we'll stop here. And let's see. So I'm Eric and you're Sam, and we are the Boltzmann Brains. Thanks for listening.